In this presentation, we will discuss various aspects related to generalization of predictive models. We will discuss some of the common reasons as to why some predictive models cannot well generalize beyond the training data, and will introduce counter strategies. If you recall, generalization is a term used to describe a model's ability to react to new data. That is, after being trained on a training set, a model can digest new data and make accurate predictions. In other words, all what matters is the performance of the model on the out-of-sample data set. Note that in-sample or resubstitution error rate can indicate potential model underfitting but not overfitting, since an overfit model may perform very well on the training data since it has been adapted too closely to the training data. Here you can see 4 common causes that limits the model's generalization capabilities. More specifically, we will discuss issues arising from using non-representative training data, as well as model overfitting, concept drift, and finally variations of data profile over the time. Let's start by discussing the effect of using non-representative training data for our predictive model. In order to generalize a model well, it is crucial that the training data be an accurate representation of the population. In other words, each time a new sample is derived from a population, it is crucial that the sample paint an accurate picture of the population. A training set of data must be representative of the cases you wanted to generalize to. It is, however, harder than it sounds. If the sample is too small, you will have sampling noise, which is the non-representative data as a result of chance. But even large samples can be non-representative if the sampling method is flawed. This is called sampling bias. In other words, the sampling might tend to favor to select a portion of the population and thus might not accurately represent the true population. Exploratory data analysis, or EDA, combined with the knowledge of the domain, can be used to show if the training data is non-representative of the population. Moreover, as we will see, we can use stratified sampling to ensure that our training data is representative of the population. Now let's talk about model overfitting. As we saw earlier, models overfitting is another major source of models' lack of generalization. Overfitting occurs when the model starts picking too much details that are likely to be due to noise from the training data. Overfitting the data is when the model has been tried to perfectly fit the training data. That is often done by force fitting and is generally too good to be true. Generally speaking, models are likely to overfit when the size of the training sample is small and the model is too complex. Now let's discuss the problem of concept drift. Concept drift in machine learning and data mining refers to the change in the relationship between the input and output data in the underlying problem over the time. In other words, when there is a concept drift, the statistical relationship between the input and the target variable, which the model is trying to predict, change over the time in unforeseen ways. As a result of this change, the model becomes less accurate and relevant. As an example, consider a classification model that attempts to classify borrowers based on their creditworthiness and approve or reject their loan applications. Evidently, a model that is trained during a time frame when there was no economic recession may not perform well during a recession, since customers' behavior and their loan repayment may change during a recession when the unemployment rate increases. For example, the graph on the right-hand side shows the historical loan default rates, over the time where the default rate is shown to increase significantly as a result of economic recessions, as shown in yellow in the picture. Now let's discuss the effect of changes of data profiles over the time. In addition to the concept drift, which refers to the changes in the relationship between the input and target variables, the data itself can change over the time. This can result in poor and degrading predictive performance in predictive models. The change to the data could take any form, including, for example, a gradual change over the time, a recurring or cyclic change, or a sudden and abrupt change. A good first-level intervention is to periodically update your static model with more recent historical data. For example, perhaps you can update the model each month or each year with the data collected from the prior period. This may also involve backtesting the model in order to select a suitable amount of historical data to include when refitting a static model. In some cases, it might be appropriate to only include a small portion of the most recent historical data to best capture the new relationship between the input and the output. Now let's discuss 4 common strategies to enhance models generalization. More specifically, we will discuss how increasing the training samples, stratifying our training set, models regularization, and early termination of the training process can enhance models generalization. Let's start by discussing the effect of the training sample size. Data is the fuel needed for any successful predictive modeling exercise. As we saw before, increasing the sample size reduces the likelihood of overfitting. In other words, the gap between the training error and testing error starts to narrow as we have more sample in our training data. Intuitively, it becomes more difficult to pick arbitrary random noise from the training data when there are many training samples. Now let's discuss stratified sampling. Imagine we are running a survey in the US that records the education level and median income of a specific state. If we only question people that live in expensive districts, we would surely introduce significant bias in our sample. Thus, we need a way to select people of any economic status so that it roughly approximates the corresponding distribution of the population. This is exactly where stratified sampling comes into the picture. In a stratified sample, a researcher divides a population into homogeneous subpopulations called strata based on a specific characteristics such as race, gender, location, etc. Every member of the population should be in exactly one stratum. Each stratum is then sampled using a probability sampling method such as cluster sampling, allowing researchers to estimate statistical measures for each subpopulation. Stratified sampling makes the training set to be a good representation of the actual population and addresses the representativeness aspect of the training set. As a result, models will be able to generalize better compared to when the training sample is non-representative of the underlying population. Now let's talk about early termination of the training process. Many of the statistical models, such as the popular neural networks, are trained iteratively. This means that the model tries to enhance the estimation of its parameters in several iterations or steps. However, as the training continues, models also start to overfit. As such, early termination of the training process is an effective strategy to avoid overfitting. Of course, we can't do early stopping using the test set because that would be cheating. Instead, we would determine when to stop by monitoring the validation error during the training. Unfortunately, however, implementing early stopping is a bit harder than it may sound. The reason is that the training and validation error fluctuates during the training, so it is hard to tell whether an increase is simply due to those fluctuations or not. Finally, let's talk about the concept of regularization. Regularization attempts to improve a model's performance by simplifying it. So far, all of the cost functions that we have discussed have consisted of an average of some loss function over the training set. Often we want to add another term called a regularization term, which penalizes the model that are somehow complex and are unlikely to generalize well. The figure on the right shows an illustrative example of a regularization for a logistic regression classifier. The initial model tries to classify all training data correctly. As such, the decision boundary has been changed so that the two red data points on the top of the figure are correctly classified. This has created a rather complex decision boundary shape. After applying regularization, the decision boundary has become like a simple circle where red data points are inside the circle, despite that some training data sets are misclassified. Generalized linear models such as lasso and ridge regression are among the best examples of applying regularization to simple linear models. These models are discussed in details in the next module.